All right, so let's move forward, and now we'll talk about how we can train these networks. Okay. Now just let's do a recap. I think we'll just move fast on this because we just covered this. And so your convolution layer is nothing but you have some set of kernels. Sorry, excuse me. Okay, so you just have some set of kernels which you apply on your input image or a feature map, and then they give you some kind of output which is like used to form the feature or activation map for the next layer. All right, so we need these parameters to be learned, which we call filters. In this case, these 27 values. So when we say we are training a network, what exactly we are trying to do is we're trying to learn these values. And we learn these values based on what problem we are solving and what kind of data we have. So depending upon that, these filters will be different. And sometimes it happens that if two of the problems are correlated, then what you can do is if you have a large scale data set for one of the problem, you learn these filters for that problem, and then you can use those filters for the second problem where you don't have that much data. So we call that transfer learning, and we also call that fine tuning. And I think you are going to do that a lot if you are doing a deep learning based course project for this module. Okay. Now, this was simple like using the known kernels, and we know this is like kind of detecting edges, but we want to learn these kernels automatically. And here I showed you like some examples of like learned kernels and what kind of activations we are getting after applying those kernels on the input feature map or the input image. Okay, so now let's talk about how we can learn these kernels. So this is a general architecture of a standard convolutional neural network. You have an input image, you have these convolution layers, you get these feature maps, and you will have some more of those layers. Finally, what you do is, depending upon what problem you are solving, let's talk about classification, you will have some predictions. All right. Now, what you want is you want those predictions to be exactly what you have in your ground truth. And we talked about ground truth and network prediction, I think, in second or third lecture. So prediction is what the network is telling you, and ground truth is the actual label about this image, which you already know. Okay, so this is called like a supervised learning strategy. And we also talked about this earlier. So what happens is for each image, you know what object is present. Okay, so we call that annotation or label. Now that is your ground truth. And then there will be some prediction which this network will make about this particular image. Now, based on what this network predicts and what's the ground truth, we determine how good this network is doing. All right. So, for example, if this network can predict there is a robot present and the ground truth is also a robot, then we know the network is performing pretty well. And it's performing means it has certain weights in these layers, right, in forms of those convolution kernels. It means that it already knows what weights are required for those kernels to do these transformations because it is able to predict it correctly. And it means that we don't need to train it anymore. Okay. Now, the network might predict a bad prediction, or it might perform very poorly. It might say there is no robot in this particular image. In this case, we know that whatever weights we have in these kernels, they are not the right weights. It means they are not extracting the right set of features which we want to make this prediction or classify this particular image. So then what will happen is we will have some kind of notion to say that the network is performing very badly, and we call that a loss function. Okay, so based on what the ground truth is and what you predicted, we will estimate, okay, this is a poor prediction, and then using that estimate, we will try to update the weights of these kernels. All right, so we'll make the updates such that the network is then in the next iteration able to perform better than what it was doing in the previous stage. All right, so that's the training process. So this you have seen earlier. Given a set of images, we call these training images. All right, so these are the images which we will use to learn those weights. And in this case, we are using a CNN, so we don't have a separate step for image features. Your CNN is going to do that. Now, what will happen is for each of these training images, you will know the exact label. All right. So what you will do is you will send this image or each of this image in the training set to this network, make a prediction, and based on how the network is predicting, is it a good prediction or is it a bad prediction, you will compute some kind of loss here. And if the loss is pretty low, then you know your network is already trained. So you will call that a trained classifier and use it for testing. And ideally in testing, if it's a good classifier, then it will be able to predict that there is an apple present here. All right. If the prediction is pretty bad and you're getting a very high loss, then you will still train this and you will try to update the kernels, the weight of the kernels in your network. And that we call training, and we'll keep doing that unless the predictions are like are pretty good. Okay, so we'll keep doing that. So we'll keep passing these images and we'll repeat the process. And that's why we have these training images. So we use them for training the network. Okay, so I said like we need a loss function to estimate how good our network is predicting, right? So when we say how good, we mean like in terms of prediction, what it should be predicting and what exactly it is predicting. And the network training, like the update we make to the kernel weights, we call that optimization. Okay, so the goal is like we want to find the best network parameters. In this case, like the best kernel weights, which can extract the right set of features such that we minimize this loss. So okay, so let's say your CNN or your architecture, you name that F, right? Because at the end it's a function. It's a function because it takes image as an input and it will make some prediction. All right, so you can represent your network as a function F, and input in this case is like image, and W here is another parameter to the network. We call these network parameters, and these parameters are like all the kernels which you want to learn. So given some set of kernels and given set of input, the network will make some prediction, right? That will be F of this image and these weights. Now, based on what the network predicted, and this is the ground truth, which should have been predicted by the network. So you will use these two values and you will define a loss function, right, based on how close this predicted value is to this ground truth. And what you do is, since you are not training using just one image, you are training based on like a lot of images, right? So let's say you have n images in your training set. So you will repeat this process for all the images starting from 1 to n, and then you will compute the loss function and then you will just normalize it. So this is the loss value of your network, and it's going to tell you how good your network is doing. All right, now we'll see like what this loss function can be. So we will let's for now just assume that we have a loss function which can do that. Okay. Now let's say if we have a loss function, what we want to do is we want to minimize this loss value. So if this loss value is close to 0, it means that a network is predicting perfectly what it should have been predicting, right? So then the goal is we want to minimize that cost, which is given by that loss function, and that is called network training. And what we can do is we can use a gradient descent algorithm for that. And I think you all must already know what gradient descent is, but I will still give you like a brief overview how this works. So the idea behind gradient descent is, given a function and some parameters of that function, what you want to do is you want to minimize like the cost or the final output of that function. Okay, so for example, let's assume that you have a one-dimensional function. In this case, it is f of x. So the input is x, this x direction, and it predicts some value. All right, so this is your function. Now, what you want to do is you want to minimize the value of this function. So if you will minimize, what will happen is you're trying to figure out what is the value of x for which this function has minimum value. So in this case, you know this point, right? So value of x at this point is something which you are looking for. And if you take the analogy back to your network, what you wanted is your network will have some parameters, those kernels. So the goal is to find such values where you get this minimum. And again, so this is just one dimension, but you can easily generalize this to n dimension because your network has multiple dimensions, right? It has so many kernels, so many weights. Now, what will happen is, so this is like how gradient descent works. Let's say you start at a random location, in this case, A1, all right? So you will put your A1 as an argument to this function, you will get this value. And similarly, in your network, what you do is you randomly initialize your kernels. Okay, so that's the analogy, just keep track of that. So you initialize this value x randomly using this A1. Similarly, you will initialize your weights randomly. So in this case, you get this point, but in your network, if you initialize randomly for each image, you will get some value. All right. Now, what you want to do is you want to move this point A1 close to this. So how you can do that is you can try to move this point along this line. And a nice way to do that is you can compute a gradient at this particular point, right? So gradient, if you find a derivative of this function, it's going to give you the slope at this point. So it will be something like this, all right? So you find the gradient, this orange line is showing you the slope. Now, if you move in the direction of this gradient, then that can lead you to this low point, right? So there's a question, let me finish this. I will come back to that. Now what you do is you update this point A1 and move to A2. And the way to do that is this simple step. You find the derivative of the function, that's slope, and you have some parameter here, so gamma in this case. It tells you by how much amount you want to move. So that's your step size. And we call it learning rate. So you will talk about this a lot when you're training your networks about this learning rate. So this gamma is your learning rate. And what you do is you subtract this value from your A1 value. All right. So let's see why we are subtracting. Now at this point, when you compute the gradient, so this is a negative gradient, right? Because the slope is towards left. If you compute a gradient at this particular point, then that will be a positive gradient. Okay, so at this particular point, it's a negative gradient, and you want to move towards your right hand side, towards this direction. So you want to add something to this value, but you're seeing that the gradients are coming of negative at this point. So what you will do is you will use a negative sign that will make the gradient positive. All right, and then whatever you are adding, you will add up values, right? And then you will move towards right. So if you had a plus sign here, then you would be moving towards your left, but that's not what you want. You want to move towards your right. That's why the negative sign, then gamma, and then the gradient value. So gradient is like the slope. If the slope is pretty high, something like this, then you will have a bigger step. And that's about right, because it means that you will move pretty fast. Okay. Now consider the same scenario when you were at this particular location. So in this case, the gradient will come up as positive, right? But you want to move towards your left, which means you want to subtract that value, and which is perfectly fine because you already have a negative sign here. All right. So then that's the first step. You move to this particular location. Then again, you find the derivative at this particular location. You find the gradient, and again you add that value, A3. So you might be observing that as you are getting closer and closer, the value of your gradient is decreasing, right? It started like this, so which is a high gradient or a high slope, then it's getting lower, which means that you are then the whatever values you're adding to your point, they are getting smaller and smaller. So your step size will reduce. So as you move closer, your step size is going to be very small. Okay. Now at the end, what will happen is as soon as you reach at this point, then your gradient is 0 because this will be just a horizontal line. And this will be a 0, so it will give you the same value, which means that you are already at your minima, so you can't move any further. And that's where you know that whatever loss function you have, you are not going to move anywhere from that point onwards, and then you stop. You know that you already found what you were looking for. Okay, so you will stop at this point when you're not making any progress. So now let me see, like we have a couple of questions. So from Doyang we have, can we just do the derivation? I don't know what you meant by this. So we are computing derivatives and we are taking like one small step at a time to move to that point. So what do you mean by when you say, can we just do the derivation? So can you reformalize that question, Dayon? Derivation of the function maybe. So yeah, so that's what we are doing, right? We are computing the derivation of the function, and based on the derivative or whatever value we are getting, we are moving our point in this curve, and that will lead us to like the minima or the point which we are looking for. So Dayon, did that answer your question? Because I'm not sure. Okay, so I'm not sure what you missed. So let me like quickly repeat what I just said. So you will have some function, right? And again, this is just a function in one dimensional, but you can easily generalize this to n dimensional or multiple arguments. Okay, so you plot this function. In this case, this is your function, and you have to reach this point where your value of loss is like minimum. But you don't have like any other knowledge about this function or these values x. So you don't like you can't just directly reach to this point. So to reach that point, what you do is you randomly start from a point. Let's say it could be at this point, it could be here, it could be anywhere. It could be in fact like at the same location. Okay, and then you compute derivative, and then based on that derivative you will move around, like whether the derivative is positive or negative, you will move towards left or right. Okay, all right, it's great. So another question from Rahul: how to ensure that we always arrive at global minima? Yeah, I think that's really a good question. And so with gradient descent, if the function is non-convex, and that's the case like for most of the computer vision problems which you are going to work on or which we are solving, so all the functions are non-convex. So we can't guarantee that you will reach like a global minima. So it could happen that if you would have started at this point, you will end up at this location, which is like a local minima. So if you started at this point, you will never be able to reach this location. And but if you have a convex function, so convex function is like something. A good way to explain convex function is if you take any 2 points in your curve, and if you draw a line across those 2 points, then any point in your curve between those 2 points should be below that line. Okay, so let's say I pick this point and this point. If I draw a line, then all of these points are below that line, right? So at this, from this point to this point, this function is a convex function. But if you look at here, if I draw a line from this point to this point, so these points are above this line, right? So that's why, so this whole function is non-convex. So Rahul, did that answer your question? And of course, I mean, there are many ways. to ensure that we don't stuck at these points. And probably I don't think we should cover that in this class. So Furkan has another question. If we continue the derivation plenty of times and amount all of the results, we can pick the lowest minima, correct? Yeah, so that's like one solution. And the way we do that is we do that multiple times with multiple or with different randomly initialized points. And we assume that at least like at some point of time, we will get to the local minima. And there are like different ways. That's a research area to get like to a global minima and non-convex functions. Okay. All right. So yeah, that's how a gradient descent works. Now, what you should try to do is try to visualize this function as like your network. Okay. So this function is not just your network, it's actually the loss function which you apply on your network using whatever the network was predicting and what the ground truth was. So you will have a curve something like this, but of course that curve will not be like a 1 or 2 dimensional curve. It will be multiple dimensional, and also like your input will be not just a single variate, it will be multivariate function. And what you can do is for each image, you will get a value something like this, and then you can try to reach this point. Okay, so ideally what you do is you don't compute these gradients or travel along this curve using just one image. You compute the gradient like across all of your data points, the equation I showed you earlier. So you just average the loss value and then move along that curve. And then the assumption is that we will reach such a point where the network starts to predict better. All right, so yeah, this I think we already covered. It is used as an optimizer for functions, and if we have a convex function, then it's guaranteed that we'll find the global optimum. So this is like one simple example of a convex function. So as I explained earlier, if you pick any 2 points in this curve and draw a line, then all the points between those 2 points will be below that line. Okay. But in case of non-convex functions, which we have like in our computer vision problems, we will find a local optimum. And that's example of a non-convex function we saw earlier as well. And as I said, most vision problems are not convex. So this approach will work on multivariate function, of course. And instead of like single derivative, we'll have to compute partial derivatives of the Jacobian matrix. And this you saw like when you were computing edge detection, right? So for computing derivative in your images, you were computing partial derivatives first in the x direction and then in the y direction. Now let's see like how we can use this gradient descent to train our CNN. So you will have n training samples, and this could be like n training images. So xi is your image, yi is the correct label, okay? Because this is supervised learning. And then fx is the feed forward network. You will use your image as an input and it will make some prediction. And then you need a loss function. The loss function, the input will be images. You need like the correct labels, and then you need the network parameters. So you could have also written this as like f here, which represents your network, but theta is representing like all the kernel weights you have in your network. And this loss function should measure like how good your network is performing. For example, if it's classification, then how well it's like performing classification. And this performance is measured only on the training examples, okay? And based on like whatever network parameters you have in your network at that point of time. All right, so I think this we already covered. So for your training data, you will evaluate how well your network is doing. You might end up at this point. Then you will try to move that prediction or that network towards your right, and that will be your stopping point. Okay, so I think we can end it here today. So because I don't think we'll be able to finish it all the things today. And let's break it here, because loss functions, then it will give you some more idea about this. So you don't need any continuation. I don't want to break like at some point where you need some continuation. Okay.